Welcome, everybody. Welcome to watch this video. I'm John Joe, currently assistant professor at Geochemical University. Today, I'm going to present the research we are working on this year on the geochemistry data mining project, occurring right here at Geochemical University, Hangzhou, China. There we go. First, overview, a brief introduction of the university. At Geochemical University. So we are a university with a global vision and with a global mission and with the goal of becoming one of the most competitive universities in the world. So we have a very broad international collaboration with over 100 institutions in different countries in the world. So a glance of Georgia University, we have over 50,000 students. Among them, half of them are graduate students. And this year, 2020, we have over 4,000 faculties in the area in science, arts, engineering, and social sciences, arts, and physical education. And also we have, among the students, we have about 10% to 15% of them are international students from various different countries, and we are one of the leading institutions in China. We hope we would like to be one of the leading institutions in Asia, and we would like to be more and more competitive in the university ranking in the world, as well as its influence and reputation, and that is our goal. So for this project, in terms of the geology data mining, so it was developed under the idea from the International Union of Geosciences that they initiated a project called Deep Time Digital Earth in the year 2018 with the goal of creating or constructing a database that including all the data relevant to earth sciences with geosciences and could be shared with the scientists and engineers around the world. However, this project has to start from scratch, so we are one of the institutions that are moving one step forward. So before we move forward, let's take a brief view of what people in earth sciences have already achieved, since many of the audience watching this video are not earth scientists. So there were a significant improvement of understanding of our planet in the past century. So in part, for example, we have explored the land and the sea, and therefore, it was one of the great theories in geosciences, such as the theory of plate tectonics, was initiated by that. And during the same time, or time after that, this was in the 1960s or 70s, and this was in the 1970s, as well as in the 1980s, that for the polar mission brought a lot of samples back, and the earth scientists spent many efforts in constructing a lot of analytic equipment in geochemistry to analyze the samples. And in the end, those similar equipment were used to analyze Earth's data, Earth sample, which greatly improved our understanding of the formation and evolution of the Earth and our sisters and brothers, such as the Moon as well as other planets. And also, Earth science made a great contribution in understanding how the Earth became a habitable planet. One of the studies was to analyze the carbon dioxide concentration in the atmosphere. And nowadays, we all know that the carbon dioxide is a greenhouse gas, and therefore, the global warming or global climate variation is a critical question that to face human civilizations have to face in the 21st century. And meanwhile, there's another very important development in the human society, that is in the information technology, represented by Moore's law. In this plot, the horizontal axis is the year. So in the early years, when the child of air the company was born and built the first semiconductor, and later on, when the time goes on, for the price quality ratio, we back to the call of the computer chips that was being created. It followed a law which is called the Moore's law. That is, for every 1 year or 2 years, its price quality ratio that improved for 2 times. So therefore, it's very amazing to see it has increased to many orders of magnitude since the beginning of the year, beginning of the semiconductor industry, or the information technology industry. So for Earth scientists, not only we look for ourselves in this 21st century, but also would like to land on the moon, such as China landed on the outer side of the moon. in the last year, and also China will land a human on the moon probably in the next 15 years. And for the Mars, similarly, is very likely the very first human sapiens that ever landed on Mars will come from supported by NASA. Probably that will occur in the 2040 or 2050. So we are looking forward that within our lifetime we might see a live human that land on the moon and hopefully landed on the Mars and coming back. And meanwhile, we will have more and more Earth data as well as data from the planets. So we need to process this data to get us from different understanding. So if we look at the evolution of how Earth scientists improved, at the very beginning, people only focus on the field work. And later on, when we have more analytical equipment, we began to not only have the field observation, but also analyze samples in our labs, analyze their major elements, trace elements, and the isotopes, and also do various high-pressure experiments or low-pressure experiments to understand the process that occurred that could be matched with what is going on in the field. So with the development of the computers, people began to numerical simulations such as geodynamics, such as first-person calculations to calculate the mineral structures or the various physical chemical properties of minerals, or we have the other thermodynamic simulations such as software such as MELTS that help us to understand the evolution of magmas as well as the crystallization process. And now in the 21st century, in the year 2020, we have already moved into the era where we not only have to do field observation, laboratory measurement, numerical examinations, but also we would like to introduce the idea of data science and use artificial intelligence to analyze this data to provide a very different perspective in understanding the Earth's formation and evolution, as well as the relevant questions in the planetary science and in astronomy, which is highly connected to Earth science nowadays. So for the questions we would like to answer for the very beginning of several projects relevant to the volatile cycles of the Earth. And the volatiles, what we mean here in geology, is the elements, are the elements such, for example, hydrogen, water, carbon, nitrogen, sulfur, and phosphorus. For example, it's the air that you breathe in. But according to Earth scientists, most of the volatiles do not exist in the Earth's atmosphere, but they also exist in the Earth ocean, but a significant proportion of them in the Earth system locates in Earth's silicon mantle, or even in Earth's metallic core. Here in this figure, on the east side of it is our current Earth today, which is operating with a plate tectonic system, as well as modern atmosphere and ocean circulation system that volatile cycles between each sphere and between different spheres. However, in the early Earth system, which is very different from than what it was going on, and it was very inhabitable for any kind of life at the beginning, it was in extreme conditions. But the volatiles were carbon, hydrogen, sulfur, nitrogen, and phosphorus also circulated along this system. So it is pretty interesting, another story that was operating in the early Earth system that we are interested in. And in order to understand these questions, so Earth scientists, we do a lot of field observations. And meanwhile, we also create a lot of physical and chemical models, which are mainly from the laboratory experiments, as well as the numerical simulations. So to have that in this particular project we're trying to do, then we are trying to answer the data by database. So what the original raw information we got was the organic and inorganic Earth materials in terms of their chemical composition, their crystallography, and their molecules, as well as this spatial temporal distribution in the geologic history. So we combine this information in the huge database, and for this database, or spreadsheet, if you can call, which composes of millions of data, then we use various statistics, machine learning methods, or applied mathematics to analyze them and realize these mathematical ideas with different codes, such as R, MATLAB, or in particular Python, and in the future C++, and we do that on the personal computers or on the cloud, and in the future we also do that on the supercomputers. So this project was initially initiated by the dean of our school, Professor Junke Xia, and he sponsored our initial funding in doing this project. as well as personnel to kick the project off. So among it is supported by three important aspects. One aspect is geosciences, that we geoscientists are most familiar with the questions we're trying to ask, and that's leading by me. And then we also have the data scientists. For example, Ren Junxu is from the Data Science Center at Zhejiang University. He got his PhD at UC Davis and worked for 7 years at the Visa for data science and then artificial intelligence, a common Visa in the Bay Area, San Francisco. California. And Cao Qi is working in a financial company for deep learning right now. And also we have two computational people that provide support for us. So we have this is a triangle supporting team to make the system goes on. So in the past 3 months, we have several projects already began and almost finished. For example, the very first project that relevant to the Earth's hydrogen preservation question, the paper is already in review process. We also questions relevant to the redox state of the Earth's clinopyric sink that Wei Hua Wang and his PhD advisor Professor Yang Yan are working together. I think they are pretty close to writing the paper, as well as our Dr. Wang Lu and working with Professor Wang Qingyan in terms of lithium mecha question. I think they're also writing the paper now. And the two of my PhD students are working on diamonds as well as carbonate. And they're also trying to wrap it up. And we hope all of them could submit their paper in the year 2020, if not in the or before the Spring Festival of 2021. So right now, there are 4 active science projects that are going on right now in their program today. So they are about the hydrogen, more questions about hydrogen in the peridotite. So there are about the different molecular biologies questions that are leading by Dr. Tao Heyu, who is a postdoc right here and working with the postdoc advisor, He Ding. Sorry, I make it wrong. This should be He Ding. And Natasha, visiting master student, will come to work with me next year, and she's leading a project relevant to Garnet. And then we have Luan Kang working with Professor Liu Jia. They are targeting a new question relevant to the igneous rocks processes and global climate in the Circum-Tibet region. So not only that, we do have very strong tech support teams. So we have 4 tech support teams, and one group that focus on the Internet of Worms. So they get almost 1 million publications in terms of the Titan abstracts that will dramatically improve the efficiency when we search publications, since that's where the tables or data is coming from. The reason why we do not use Google is not because we don't use Google. We use Google, but the problem is that Google search all the information online. It's very hard to match the exact information you want. And if you search by Web of Science, the problem is that there are tens of thousands of journals in the Web of Science, and most of them are not relevant to geology. So we focus on about 1,000 publications, journals in geology, and we try to mine about 3 to 5 million publications from these journals in English, in Russian, in Chinese, and in Japanese. So there's 4 major languages that with the different geology journals, and we are moving forward with that. And also we have one group that are doing statistics, that mainly using R to achieve their goal. And we have another group that mainly use Python and MATLAB, and they are developing various machine learning tools. And then we have another group that we hope that all of you will run by your own personal computer for any calls that is more than 15 minutes. You should not run on your own personal computer. You should be run by the Huawei Cloud, which is leading by Zhao Jiahua, who currently will begin as a master student and a graduate student at Padova University, Italy. So here is some more introduction in different groups. So we have very diverse group coming from different institutions around the world. So a great effort has been made in Internet of Worms. Now we have become more and more efficient in targeting different journals. And in future projects, if the project is interested in particular one journal or two, we will set it as a priority for the Internet of Worms teams to do that. And we also have a statistics team, which is leading by Hu Dan now from Notre Dame, previously by Gu Yu, and we are trying to solve all of your statistical problems. And soon we will have the head of the Department of the Statistics at the Zhejiang University, Professor Zhang Peng's group. They were involved. He will come with his PhD students into that statistics. We also have a machine learning team. They have developed various tools such as, let's say, XGBoost, such as SVM, such as neural network, very neural network methods, or random forest, etc., and to modify the source code so that it's more applicable to the questions that we're trying to address in terms of geochemical questions. And also we have a cloud computation group that they maintain our codes at Git or Git, and we're moving forward pretty well actually. So this is one example of different codes that we have. Actually, we put them like Git, and we want to make it a public and open source so that people from around the world to access it. And here is the computational source that we currently have. We run it by Huawei Cloud. So though we have about 12 cores, we could run 5 subjects at the same time. That means we have 60 cores, which is not a lot, but currently for the data that we are trying to work on is okay. In the future, we're going to move on to the supercomputers or much bigger clouds that I currently have, and I'm very fortunate we do have a different support for the cloud team. Okay, so to make an analogy, what we do actually is not fundamentally different than what the previously people have done. For example, geologists, we collect samples in the field, or we squeeze them into high-pressure experiments, or we get these samples from some of our other colleagues. Then we prepare the samples. Then we do that. After that, we use different analytical geochemical tools to do it. For example, we use electron microprobe analyze the major compositions. We use the Flores transform IR to analyze their different volatile compositions, and then we use the laser ablation SVMS to analyze the trace elements compositions, or we use TIMS to analyze the isotopes compositions. So for each compositions we analyze, we need to have equipment, which is a tool, and then we also need methods, which is a software. Basically, you run this equipment. And here nowadays we do the data science to work on the geochemistry questions. We have to build a database, which is basically our samples here. And so we have to collect this data, which is extremely helpful when we use the internet worms. We don't get PDFs, we only get the title and the abstracts, which is okay because that is public. You don't need to have any, like say, authority or proof to get that. It's okay. And then we analyze or clean the data, which is not fundamentally different than the data preparation. For example, if you want to do electron microprobe analysis, you must have a thin section so that is flat for the samples, because that is what is required later on by analysis for Bragg's diffraction law. And so we have to do data cleaning. So this is corresponding to this traditional work we have done. And here we use various applied mathematics, such as statistics and machine learning, and then we ran it by the on our cloud or on your own personal computer if the calculation is pretty fast. So this is mathematics here is equivalent to the methods people have used before, and the equipment people have is equivalent to your own computer. Your computer is equipment, and the cloud is just many computers that are parallel together. So by that, we're not fundamentally different than what is going on. So that's the end of my introduction. I hope that you get an overview of it. And next week, I think the very first speaker, Dr. Chen Huan, is going to present what he has achieved in the very first question. Actually, that paper is in review now. I would like to show you more about the different science we've done. So with that, thank you very much for watching, and have a good day.